AirPhoton is the American division, the instrument division of Grasp Earth. And this is the first in our webinar series on the science of particulate measurements. Today, we're going to be presenting the work of Dr. Chong Li on obtaining PM2.5 mass in near real time from optical measurements. And if you would like to access a recording of this webinar, we'll be emailing out that information at the end. So, okay, I see I am already missing a slide. Here we go. All right, so first I wanted to introduce Grasp Earth. So Grasp Earth, some of you may know us as AirPhoton, which, as I mentioned, is the US-based manufacturer of instruments. We've been around since 2012, and we are also Grasp, and Grasp is a French developer of inversion software for particulate cloud and surface characterization. Grasp started in the year 2015. And 2 years ago, we became one company, Grasp Earth. And if I have to say what unifies Grasp Earth is that we are dedicated to advancing the monitoring of Earth's atmosphere for human health and climate change applications. And we do this in a variety of ways, from ground instruments through space payloads and observations, and through all of the things which Grasp can do in terms of combining data from multiple sources. Now, I just wanted to run back up here for a second and talk about why is obtaining PM2.5 mass in near real time important. And well, don't we do this anyway? So many instruments will give you estimates of PM2.5. The difference is that nephelometers are a lot more accurate and sensitive in their measurements than a lot of the particle counters that are used to do that. But we always collect our data under ambient conditions. And so those people who want to know PM2.5 mass, they want to know dry mass. And so that's what some of the work of Dr. Li is all about, is converting this to dry mass. Near real time is important because, again, many of the instruments that do this, if you're doing it with filter-based measurements, which are the most accurate, it's going to take quite a bit of time to go from those measurements to actually getting the filters weighed, the information out there to an audience that might need that information. Okay. All right, so all of our data is coming from, Dr. Li's work is coming from the SPARTAN network. The SPARTAN network is a global particulate matter network. Their sort of mission statement is there in the slide. I'm not going to read that to you. But just in short, they are trying to provide higher quality, higher detailed information about particulates that are concerned to human health. And this is currently the stations they have, and Dr. Li will talk a little bit more about this slide later. So at every SPARTAN station, they are making the following in situ measurements. They're using nephelometers. That's the real-time optical measurement that we'll be talking about in this presentation. And they are using filter stations. Both of these instruments are provided to the SPARTAN network by AirPhoton, and the filter station provides them with the highly accurate gravimetric measurements. Also, at every SPARTAN station is a sun photometer, which is manufactured by CMIL. This gives a full column measurement of the aerosol optical depth, another optical measurement. And so the idea behind why we make these two kinds of instruments is that you can have a detailed retrospective analysis coming from your filters, but you can combine that with real-time information from your nephelometer. There's a new instrument we have which also does real-time optical measurements with more capabilities and higher accuracy than the integrating nephelometers. And again, Dr. Li will talk just a little bit about that. Current usage of the filter stations runs on a user-specified collection cycle. The samples are placed, you can see in the cartridge, which holds 8 filters. And so typically one is held aside as a control, and the others can be used to collect variety of sizes anywhere between PM2.5 and PM10. The most common is to collect PM2.5 or PM10 and not the intermediate sizes. So this is the SPARTAN sampling strategy. In each one of these filter slots, they are collecting particulates over a 9-day period, 3 hours each day. Each day, they advance the time during which they're collecting. And the reason they're doing this is that they want to progress from daytime through nighttime. They want to layer the particles to avoid semi-volatile loss. So when they do this, they wind up with 63 days worth of sampling. Now, there is a configuration of the sampling station. There's several configurations, but most commonly it's configured that 6 of these filter slots are used for PM2.5, 1 is used for PM10, and 1 is used as a control. There is a configuration of the instrument that allows simultaneous collection of PM2.5 and PM10, but that is not what SPARTAN is using. SPARTAN is using a single inlet and using that for mostly PM2.5 collection. SPARTAN has done a lot of work to ensure the accuracy of their filter-based measurements. A lot of that is done by comparing their results with the improved network in the US. Just quickly, what SPARTAN is getting, because they want to make available a combination of satellite and ground-based data, so they want to sort of expand the point data that you're collecting with the instruments over a wider area by connecting this with satellites. So what they've got here with the sumptometer, they get a scale height value, they get diurnal variation from the filter-based measurements, and then they can get the scattering efficiency from the filter measurements, as well as the near real-time optical measurements coming from the nephelometer. SPARTAN has all of their publications on their website, which is spartan-network.org. I should show that, and I apologize for not doing that. But we'll make sure that it's available when we share the slides. Just a word about the nephelometers and what we do to make sure that they're accurate. So we have an inlet where we're measuring the pressure drop within the inlet. We get a real-time flow measurement that's highly accurate. We can then provide that information to the instrument controller, and then we have an intelligent multi-speed fan, and we can adjust the fan speed to keep the flow rate stable or to change the flow rate to get different size cuts, and that is what we do. So SPARTAN uses, again, an instrument, the IN102, which can collect anywhere between PM2.5 and PM10. They're only collecting at those 2 values, as far as I know. There's another version which we provide. Some of the SPARTAN stations do have this capability, although they don't use it. That's the IN102 extended. That goes all the way down to size cuts as small as PM1 up to PM10, and from that you can get a full-size distribution. And so our nephelometers, our IMAP instrument, and our polar imaging nephelometer, again, which Dr. Li will talk about, all have this flow feedback control system. So I just wanted to show you a little bit of data here. that it gives an example of how we can separate sizes. So what you're seeing here, this sawtooth pattern, is the changing flow rates. So we use higher flow rates to capture smaller particles, lower flow rates to capture the larger particles and everything smaller. So when we look at total scattering, you can see some differences. When we look at backscattering, in this case, we can see very distinct differences between PM10 and PM2.5. And again, just showing here the capability of the extended version, which can again distinguish between PM1 and PM2.5. Dr. Li is using a graspin version. She will talk a little bit about that, but what I wanted to say is we use the graspin version because it's good at taking complex data sets with lots of information, lots of parameters, and pulling out useful information to create a product that's most useful to our users. So in the case of our nephelometer, or the extended nephelometer, we have 3 wavelengths, 4 size bins, 2 scattering orientations. That's a lot of information, but GRASP is able to handle that and pull out and create the product information that we want to provide to our users. So I'm not going to say very much. Again, Dr. Li will talk about the IMAP, but one point I wanted to make is that our optical instruments use both optical sizing and geometric sizing. So the optical sizing, that's purely based upon the light scattering of the particles. The geometric sizing, that's based on the fact that we're using cyclone inlets and different cutoff and different speeds to get different cutoffs. So that's a geometric sizing. So what we can then do, and what we're in the process of doing, is relating satellite measurements to the in situ measurements at what we like to say is nose level, so where people are exposed. So that would be the integrating nephelometers and the IMAP. I think that's all for my slides. So I'm going to stop my sharing. I'm going to turn this over to Dr. Li and let her share, and I will mute myself. Thank you, everyone, for attending today. Oh, just one more word before I stop sharing. I know quite a bit of our audience is joining us from India. I will be at the BSX meeting in Bangalore next week. If you're there, please look for me on the app, and please come talk to me. Please come say hello. And with that, I will be quiet and let Dr. Li do her thing.
Thanks, Rich, for the introduction. I'm gonna share my screen here. I believe now you can see the screen. Let me just... Okay, so good morning or good afternoon, everyone. Welcome to the webinar of GRASP Earth. And thanks, Rich, for the nice introduction. I'm Chong Li from GRASP Earth company. Today, I'm going to share our recent work about how to determine the PM2.5 mass concentration using the nephelometer measurements with GRASP retrieval algorithm. And sorry, kind of stuck. Yeah, this talk will be organized in the following contents, including the background introduction, the introduction of the method that were used in the study, and also the data set that were used, and also the result and future prospects. As we know that the PM2.5 measurements are of great interest for the air quality community, and monitoring the PM can provide us the understanding into the fine particulate matter and its potential health impact on the human beings. And in recent years, there are many studies that's trying to invert the PM2.5 from the satellite observation or the satellite products. For example, this paper in 2020 used the MODIS products to derive 1 kilometer PM2.5 over China. And in our group, we also made some development to derive the global PM map from the polder data. Satellite observation has the great advantage of monitoring the air pollution on the global scale. However, compared with the satellite observation, the in-situ measurements, such as the ground-based nephelometer, also have its own strengths. First of all, with its high time resolution, it can capture the daily or interdaily variation of the pollutants, and this could facilitate the assessment of the short-term exposure of the pollutants, which we couldn't get from most of the satellite retrievals. And secondly, since the satellite observation is observing the culinary properties of the entire atmosphere, so if we want to determine the PM information on the ground level, it will need additional assumptions to be made or more information to be provided, such as the aerosol vertical distribution. In contrast, the in-situ measurements that is locating right on the ground, so we can obtain a much more direct measurements of the ground level pollutants. So that is why in this study, I'm trying to propose a new approach to estimate the ground level PM2.5 mass concentration using the in-situ nephelometer developed by GRASP AirPhoton. And as Rich has introduced, the AirPhoton nephelometer has been deployed globally by the SPARTAN network since its founding in 2012. So until now, the SPARTAN network has collected very abundant measurements of the in-situ integrating nephelometer at ground stations all over the world, which the integrating nephelometer measures the hourly total and backscatter at 3 different wavelengths and at 2 different size cutoffs. And in addition to the integrating nephelometer data, the SPARTAN also gathers the filter-based data, which is directly from the measurements of the aerosol sample collected on the filter. And by combining these 2 data sets, the SPARTAN also provides the time-resolved PM2.5 estimates with 1 hour resolution. And the network has validated their PM2.5 estimates with other campaign, with other methods, and has shown a very good agreement with each other with quite low uncertainty. So overall, the SPARTAN network is very valuable and suitable for our development here because it provides the nephelometer measurements which we can make retrieval with. And it also provides the coincident PM2.5 data, which can serve us as a validation data sets for our study. In this work, I used a new approach that combines the GRASP aerosol retrieval algorithm with a machine learning method. The GRASP retrieval algorithm, which stands for Generalized Retrieval of Aerosol and Surface Properties, is a very versatile open source algorithm, and it has been applied to many different remote sensing measurements, including passive, active, or spaceborne, or ground-based, etc. For example, here I list most of them. You can see we have been applied to polder data, to AHI imager on board of the geostationary satellite Himalaya 8. We also applied them on the LiDAR data from the ground or from the space. And in our study, we use GRASP to retrieve aerosol properties from integrating nephelometer. And apart from GRASP, we also integrate a machine learning method. Machine learning, we know that now it's becoming very powerful and popular tool that can bring us extra advancement, especially in the area when it is very challenging to establish a physical model. So the machine learning method I use in this study is known as gradient boosting machine, which is developed by Friedman in 2001. And since then, it has been applied in different fields, including the atmospheric science. And I will explain this in more detail for later. So here is a simple illustration of the general structure of the inversion algorithm of GRASP. And you can also check on our website to know more detail about it. And also we provide a GitLab repository for downloading the code. So basically the algorithm consists of 2 independent modular. The forward model, which can simulate a variety of remote sensing observations, and it allows for flexible adaptation to the information content provided by the instrument. So for the case of nephelometer, the forward model will simulate the aerosol single scattering properties. And the numerical inversion modular they use the multi-term least square fitting to invert different remote sensing observations as well as their combinations. In the case of nephelometer retrieval, GRASP will take their measurements as input, which include the total and backscattering at 3 different visible wavelengths and at 2 different size cutoffs. And it also provides the following retrieval outputs: the aerosol size distribution, and also the real and imaginary part of the refractive indices. And for people who are not very familiar with the aerosol optical properties, so basically the aerosol refractive indices is a measure that describe how light interact with aerosol in the air, and it has real parts and imaginary part. The real part shows how much light refracts when it passes through a aerosol particle, and this will help us to identify the type of aerosol, such as dust or smoke or sea salt. And the imaginary part of the refractive indices represent how much light is absorbed by the aerosol. And this is very important to understand aerosols like soot or black carbon, etc. So together, these two parts will provide very essential information for us to identify the aerosol type. And apart from that, we also provide the retrieval residual, which is basically an indication about how well we fit the data, we fit the measurements. And in GRASP, depending on the information content provided by the instrument, we also retrieve with very different complexity of the parameters. For example, for much more advanced observation, we can use 22 triangular beams to describe the size distribution, like the AirPhoton style. But for much more simpler observations, such as the integrated nephelometer data that we are talking about here, we can just use a bilog normal model to describe the size. And in this way, we can reduce the parameters that needed to be retrieved and help us to obtain a much more stable retrieval from such simpler observations. So to start with, we did some synthetic tests to evaluate whether integrated nephelometer will have the capability or the potential to retrieve aerosol parameters accurately. And I did the simulation test for 4 different kinds of aerosol, including the biomass burning, dust, oceanic, and urban. And the results have shown that the key parameters, including the real and imaginary part of the refractive indices, as well as the size distribution, especially the fine mode part, which we are interested in for PM products, they can all be retrieved with quite good accuracy. And in addition to the synthetic test, we also apply the retrieval to real data that is collected over India. And as you can see that the retrieval shows very good fit for forward scattering and backward scattering and for different size cutoff. And meanwhile, the size distribution can also be very well captured. And based on that, I apply the retrieval method to the data that is collected from the SPARTAN network. So here I present some cases for Beijing site, and it has shown very good agreement between the aerosol parameters that are retrieved, which is indicated by the green line, and also the error measurement, which is indicated by the blue line. We can see the refractive indices are very close to each other, and the fine mode part of the size distribution also kind of have reasonable retrieval. And in general, the retrieval residual are quite low. Usually it's remaining under 10%. So from the test above, no matter it's the simulation test or it's the real measurement test, we can see that in general, we can obtain very reasonable aerosol retrievals from the integrated nephelometer data, including the size distribution. So theoretically, if we integrate the size distribution up to the diameter of 2.5, then we can estimate the volume of PM2.5. And once the volume is calculated, the only remaining factor needed to be to determine the mass concentration is the aerosol density. So For our initial attempt, I took some nephelometer data over Beijing from the SPARTAN network. I applied the GRASP algorithm to retrieve the aerosol properties, and then I get the size distribution. I integrate the size distribution to get the volume of the PM2.5. And then I plotted this volume against the mass concentration provided by the SPARTAN. And I did this for a small amount of test data sets. It's around like 100 data points. And as you can see that there appears to be a nearly perfect linear relationship between them. Then I use this inverse slope of this relationship as the aerosol density, and I applied it on a much larger data set. It's around 1,500 data points, and it performed very well as well. However, we know it's too good to be true that a single aerosol density can work perfectly all the time, even for the same location, because we know that the aerosol type change over time, so the aerosol density will change along with it. So that is why that you can see that after some time, it's around like 3 months, this aerosol density magic numbers start to fail the performance, and we start to see the discrepancy between our PM products and the values provided by the SPARTAN. So I think that the key point here to retrieve PM mass concentration from GRASP retrieval is how can we properly get the aerosol density while the aerosol density, the aerosol type is changing with the time and location. And that is why we came out with the idea not to rely on a like very simple linear regression, but instead to use a machine learning method to get the aerosol effective density. Because from the test I showed previously, we can see that GRASP retrieval can provide more or less reasonable aerosol retrieval, like size distribution or refractive indices. And these parameters should be able to give a hint on what aerosol type it is. And we are hoping that the machine learning method will be able to establish the relationship between the retrieved properties and the aerosol density. So the machine learning model I use here is called gradient boosting machine. Basically, it uses a sample of weak models like decision trees to build a stronger model in an iterative manner. And the key idea behind the gradient boosting machine is that is to sequentially train each new model to correct the error made by previous models. And then these weak models are added together to make more accurate predictions. And in such way, the gradient boosting machine can learn very complex patterns hidden in the data and handle very complex data sets. And this will improve the performance. So for the machine learning model, I provided all these variables as the input feature, including all the GRASP retrieval outputs, the size distribution parameters, the refractive indices, as well as the residual. And I also provide the integrated nephelometer measurements, which is the total and backscattering at different wavelengths and different cutoffs. And we also provide the temperature, pressure, and humidity, etc. And our target output variable is the aerosol effective density, which is basically the ratio between the PM2.5 mass concentration provided by the SPARTAN and the PM2.5 volume calculated from the GRASP retrieval. And for validation, I use leave one out cross validation. And this method, this validation method, as you can tell from the name, is that every time I will leave one data set out as the validation data set, and I will use the remaining data set as the training data set. And I do it iteratively until all the data sets have been validated. And in our case, for example, we have in total 18 sites. So if I want to predict the aerosol density for the first site, then I will use the remaining 17 sites to train a model and use it to predict for the first site. And I do it for 18 times until each site have been validated. So this validation approach will make sure that for the site we want to predict, the model has never seen its data before. And this way we will make sure that if we start to deploy a new integrated nephelometer in a new site, and this model will still be able to work. So next, I'm going to share some of the results. As here, I show the overall validation of the PM2.5 retrieval over all 18 sites. And x-axis is the PM2.5 mass concentration provided by the SPARTAN, and y-axis is our PM products. And as you can see that in general, the correlation is very high. The correlation is like coefficient is 0.84, and the mean bias is around the 3 microgram per cubic meter, and RMSE is around 16.2. And here in the bottom panel, I provided the probability density function of the bias. As you can see that overall, we can keep the mean bias under 3 microgram. And even for the very low PM concentration scenarios, for example, the red line in this figure indicated for the scenario that the PM is under 20 microgram per cubic meter, and we can still get the mean bias around 2 microgram per cubic meter. And this is quite a satisfactory result, I would say. And if we take a closer look, we took some typical sites and look into a detail. And here I show you the validation and the time series for Beijing. So we know that Beijing is a very densely populated city in the north of China, and it has very complex aerosol source, including the car emission, the coal combustion in the heating season, and also the dust storm in the springtime that is transported from the Gobi Desert, etc. So we can see that with such complex and varying aerosol type, we were still able to capture the variation of the PM2.5 very well. And for different seasons, for different time, we can all get very good agreement with the SPARTAN data. And we can have the correlation around 0.83, and it's pretty satisfactory result. And here I show the validation of the Abu Dhabi site. It's quite different from the Beijing site because it's located in the Arabian Peninsula, and it has very dry climate. It's close to the desert, so it is impacted by the desert dust very much. And we are still to have the correlation over 0.9 and the mean bias around 3 microgram per cubic meter. And here is the result for Mexico City. It's another densely populated city that it has aerosols from the car, from the industrial activities, and we are able to capture the variation of the PM pretty reasonably. And here is the result for Singapore. Singapore is also has a combination of different aerosol sources, including that biomass burning that is transported from the neighboring country, and also like local car and industrial emission, as well as the shipping emission, etc. And we can get the mean bias under 4 microgram per cubic meter, and the correlation is around 0.86. And to make a short summary here is that what we did is to combine the grass retrieval algorithm with the machine learning method to estimate the PM2.5 mass concentration from integrated nephelometer. And the result has shown very good agreement between our PM products and the PM provided by the SPARTAN network with a correlation coefficient of 8.4. And our new approach does not only give the PM2.5 products with a very high time resolution, we also provided additional aerosol parameters such as the size distribution and the refractive indices, as I described earlier. And this will provide us a better understanding of the aerosol type over the monitoring site. So apart from the application with integrated nephelometer that I just introduced, we are also looking forward to apply this new approach for other instruments. Because as Rich has introduced, the AirPhoton has designed other type of nephelometer. For example, the IMAP. The IMAP measures the element of the scattering phase matrix P11 and P12 with 8 different viewing angles from 5 degrees to 170 degrees, and it also operates at 3 different wavelengths. as we can see that it provides much more detailed information than the integrated nephelometer, because integrated nephelometer will only provide the forward and backward scattering and without polarization. And this one, it will provide much more angle information and with polarization. And we also performed the synthetic test to explore its potential, and we also see very reasonable retrievals for different aerosol type. And we performed also some synergy retrieval between IMAP and nephelometer. Nephelometer is an instrument that can measure the aerosol absorption for different wavelengths. And with GRASP, we can do the synergy retrieval between different instruments. And this may bring even extra improvement for the aerosol retrieval, as we can see from the result here. So currently, there's a scientific campaign called Luminous that is underway in Spain. This campaign is a collaboration between several institutes, including the PSI from Switzerland, the University of Granada, and GRASP. And this campaign is funded by Swiss National Science Foundation and Atmos Access. And the aim of the campaign is to gain a better understanding of the aerosol using the polarization and to understand the aerosol properties relevant to the climate and air quality in that region. And as part of the campaign, we have deployed IMAP there, which is currently collecting the data, and we expect to see the results of the campaign very soon. And another nephelometer developed by AirPhoton is PiNeph, and it's quite similar with the IMAP that I just introduced, but with even more angles. This instrument offers a wide angular range from 5 degrees to 175 degrees with a 1 degree angular resolution. And if we think of the integrated nephelometer as a bicycle that can meet our basic need, it's simple, reliable, and gets you from point A to point B. And IMAP maybe it's more like a car that provides you more advanced features and comfort. And PiNeph then is more like a Rolls Royce. It's much more powerful, advanced, and requiring specialized maintenance. And this instrument is designed for specific scientific research and can enable in-depth characterization of the aerosol in the lab or in the aircraft. And there is one PiNeph that is operated by the University of Granada in Spain, which has provided a lot of valuable measurements for investigating the air pollution events in that region. For instance, I show you here one example. In September 2022, there's a forest fire happening in the mountain of Andalusia. It's around like 30 kilometers south of Spain, south of Granada. And as you can see from the news image, there was a lot of dark smoke produced by the fire. And we can also observe it on the satellite image. This is a modest true color image for that event. You can obviously observe this smoke plume that is produced by the fire. And meanwhile, the PiNeph in Granada also captured the elevated signal of the aerosol scattering. And after we analyzed the data and performed the retrieval for the PiNeph data, we were able to clearly observe the aerosol microphysical and optical properties, which has shown very typical biomass burning aerosol characteristic with, you can see that it's with 5 mode dominated size distribution and also low single scattering albedo, meaning very high absorption of the aerosol. So as I mentioned, this instrument is designed for scientific research. So there are already several publications related to the AirPhoton PiNeph, and it has demonstrated very high measurement accuracy compared to the theoretical values that is calculated from the ME code. And it has shown also very good capability for advanced aerosol characterization when we compare with other instruments. And I'm very confident that with this instrument and the IMAP, we will also be able to obtain very accurate PM products as well. So to sum up, our proposed approach will allow us to obtain very reliable PM products from the integrated nephelometer, which shows good consistency with the gravimetric method. And we are also very eager to apply this approach to much more advanced nephelometer, such as the IMAP and PINEPh, based on their very encouraging aerosol retrieval result that has shown in the synthetic test and also in the real measurement retrieval. And here is the references that were used in the study. And here I provided my contacts and also Rich and Vanderlei's contacts. And thank you for listening. And we are looking forward to hear from you. Thank you.
Thank you very much for a very interesting presentation. I hadn't seen it before, so it's very interesting to me. We're going to stay on for a few minutes, and we will try to respond to any questions, which will be, if you would please put them in the chat if you can. There's a question that was asked at the very beginning by Yash Dahima, and it's my question too, which is, why do we need dry mass? Because the air we breathe isn't dried. Chong, if you know, please speak up. If not, I can take a stab at answering that.
Okay, from my understanding, I think that the PM concentration is reported as the dry mass is to ensure the consistency and of the data across different study, different location, and different time. So we can compare them better, because we know that the water can vary a lot from different temperature, different humidity, different atmospheric condition. And this will make it very difficult if we want to compare the PM level, right, across different site or location. And I think it's a way to control for the variability, because we know if we remove the water content information, then the measurement will focus on the solids, the particle that make up the PM2.5, such as the dust or the soot or the organic compounds or sulfate, etc. And these are the substance that affects our health, basically, I think. And yeah, so I think that's probably one of those reasons that they want to use the dry mass for the PM mass concentration. Yes, and I think also it's proposed by the EPA protocol, right?
Yes,
So,
I think it comes down to having a standard of comparison.
yeah, because like humidity can really vary from place to place.
And then can also really affect the potential particle growth depending on its, if it's hydrophobic, hydrophilic. I don't know enough about the health science part of this to know.
Because yeah, I think from my understanding, because water vapor itself, I don't think it will pose a lot of health risk as much as the component, as much as the chemical components of the PM. So if we really want to understand the exposure of the harmful particles, maybe we want to really know the dry mass instead of the ambient one. That's my understanding. Yeah.
Okay, more on this later, but because I still have some questions. But we have a couple of questions from Shreya. So her first is, all the results here that we're showing here are point-based. Can GRASS be used for a regional analysis?
Well, I would say yes. First of all, because as I introduced, GRASP is really applied in in many different remote sensing observations, including satellite, because we have like a global or regional maps of the satellite observation and satellite products, and this will help us to understand the regional situation of the air pollution. And I think in the introduction, we also mentioned that in our team, we also have made some development to derive a PM map from the satellite observation. And I would say that's pretty nice to learn about the pollution in a regional scale. And also, I would say that you can follow our following webinar because it's a webinar series, and next one will be our development about the regional analysis. It will even show you the street level pollutants, and it's very interesting. It's a combination of our method and the computational fluid mechanics. Yes, you can follow our following webinar.
Yeah, thank you, Chong. I think also I just very briefly showed a slide at the beginning of how SPARTAN uses 3 different components, one of which is the CML symptometer to get column, because this idea of using a combination of point data and satellite data, that's been an active area of research for 25 to 30 years. And so this is one of the reasons SPARTAN wants the column measurement, because they want to be able to relate it to the satellite data and expand the information beyond just a point source. And again, this is a very active area of our own work at GRASP to combine satellite and in situ data. I'm going to jump to a different question and then come back to Shreya's second question. So we have a question from Srikanth. He asks, and if I mispronounce the names, please excuse me. His question is, can you please explain the synthetic tests?
Sure. So as I explained in the
Can you
general
wind back
structure,
to that? Yeah, wind back to that.
Yeah, sure. Probably I will wind back to the structure of our algorithm. As I mentioned, our algorithm consists of 2 independent modular, the forward model and the numerical inversion. So we can run them separately. And for synthetic test, it means that, for example, when we don't have the real measurement yet, or when we want to know when we want to know the capability of the measurement when we don't have it yet, how can we make the test? Our way is that in the forward model, we can use it to simulate what measurement we will get for different aerosol type. It means that I can, in the forward model, input the aerosol properties, like their size, their absorption, etc. And the forward model will calculate what exactly measurement the PyNeph or the nephelometer will get. And this will provide us...
For instance, scattering and things of that sort, yes?
Yes, right, exactly. So it can provide us what nephelometer should be able to measure in reality. So this will create us a bunch of data set that is based on simulation. And this way we can use this simulated data and do the inversion to see if we can retrieve the aerosol properties properly. And so that is what we did. For example, here, the green line is what we input in the forward model, and the green line is what we got from the retrieval. And this way we can have a direct comparison between the input and output, and to know what's the limitation, what's the capability, etc. And this helps us a lot to understand the data if we don't really have the data yet, or if we just want to test the capability of the instrument. Yeah.
Okay, thank you. And Shreya had another question, which is, if we have very limited measurement data, how can we use GRASP? How can GRASP help us?
I think GRASP, there is a very, I would say, novel concept, is that we can use, we call it multi-pixel approach. It means that if we really have very little measurement for this pixel for this time, then we may able to combine them in different time layers and apply the smoothness constraint between different time. Because, for example, we know that the aerosol aerosol model, it won't change from 1 minute to another. Then we can apply the constraint between them. And this way it will gather a lot of measurement at different time layers and create a more enriched information between them. And this will help with the retrieval. And another thing is that when there's also like we call it interpixel constraint. It means that, for example, I can apply the smoothness between the wavelengths. For example, the refractive indices, we have 3 wavelengths, but we know that it may not change a lot with the wavelengths, then we can put some constraint between them. And this will mean that we can have a little bit less parameters to be retrieved, and this will help us to obtain more stable and more accurate retrieval, even from very simple measurement. And that is what happening with the integrated nephelometer here, because as we can see, it's not really that, I would say not super abundant information. It only has the forward and backward scattering, but we are still able to get very good retrieval from them because of the multi-pixel concept. Yeah.
Okay. Any more questions? If you do, oh, here we go. We got so Madhavan asked a couple of questions. So first question, did you make any attempts on how the limitations of angular backscattering measurements impact the retrieval of PM2.5 or PM10? In other words, have you made any attempts to make measurements from the 3 instruments, SPARTAN, IMAP, and PINEF, co-located?
In principle, yes. First of all, what's the limitation of the angular of the backscattering? That's I would say good question, because we know some angles are really important, and as we can see that from the integrated nephelometer, sometimes we really have some uncertainty in the coarse mode size distribution, although it won't affect a lot for our PM2.5 retrieval here, because we are focusing on the fine mode part. But if we want to get really a very accurate full size distribution, it can create some uncertainty in the coarse mode. But with much more advanced instrument, for example, the IMAP or PINEF there, because of the angular range and the angular information, it has really more accurate retrieval, especially in the coarse mode part. And about the collocation of different instrument, I think there is in the University of Granada, they have both PINEF and integrated nephelometer. And I think in the campaign Luminous I mentioned, there were like IMAP, PINEF, and integrating collocating at the same time. So yeah, we can also to make comparison between their data. Yes.
Yeah. Yes. So we are kind of lacking that collocated data. The PINEF is a laboratory grade instrument. There's only 3 of them in existence that I know of. IMAP is relatively new. We're just starting to get the data so we can do that comparison. We are about to ship out a couple of IMAPs to a research group in Saudi Arabia, so we'll start getting some very interesting data from coarse mode aerosols as well. The second part of Madhavan's question is, why only 4 aerosol types, that is the biomass burning, dust, oceanic, and urban, are considered?
Because inside of GRASS, we made many research, and we kind of like chose this 4 type as the most typical aerosol that is in the atmosphere. And I think these models are based on the long-term aeronet and measurements, and it's also published. It's by our group. I think it's Anton Lab. think in 2021, there's a paper. I can share in the chat later the exact paper link, and it is published, and there is all these 4 aerosol type descriptions, including their size and refractive indices, and it is based on long-term observations of the aeronet. Yes.
Okay, I think that's all the questions. Last but not least, Chong, can you zip back down to the last slide, which shows the email addresses?
Sure.
So last comment is from Shreya, who says, "Thank you so much for very insightful talks, Rich and Chong, and you're very welcome. It's what we really enjoy doing." And I also want to say thanks to Chong. And these are our email addresses. If you have any questions, please don't hesitate to write with follow-up questions. And thank you all so much for coming and joining us today.
Thank you, everyone.